Sunlight on the surface of the Pacific. Now go down. Past the waves, past the reef, past the last blue where anything green can grow. The color drains out of the water, then the light itself gives out, and every trace of warmth goes with it, into a cold and a dark that never change. Keep falling. 2.5 miles down, the bottom finally appears. A plain of mud stretching farther than any desert on land, and the mud is not empty, it is paved. Scattered across it, edge to edge, horizon to horizon, are millions of small black lumps, potato-shaped metal, each one made of manganese and iron that took longer to grow than our whole species has existed. This place has a name, the Clarion-Clipperton Zone. It sits in the Pacific, roughly between Hawaii and Mexico, and it is a prime target of the modern deep-sea mining rush. A team of scientists lowered a sealed chamber onto that seafloor. No light could reach inside. Down there, with no plants and no sun, oxygen should only fall. Animals breathe it in, bacteria consume it. The number on the sensor should have gone down and stayed down. It went up. Over 2 days in total darkness, the oxygen inside that sealed chamber rose to more than 3 times where it started. For as long as we have understood life on Earth, we have believed one thing, without exception, that every breath of oxygen on this planet traces back to sunlight, to photosynthesis, to something green catching the light. The scientists who ran this experiment think they may have found oxygen made in the dark. If they are right, one of the oldest rules in biology just cracked. If. That one word is going to matter for the rest of this story. The man at the center of this is named Andrew Sweetman. He is a marine ecologist at the Scottish Association for Marine Science in Oban, on the west coast of Scotland. He studies the biology of the deep seafloor. Back in 2013, on an expedition to the Clarion-Clipperton Zone, his instruments told him something impossible. In sealed chambers on the seabed, the oxygen was climbing. He did what any careful scientist does when the data breaks the laws they were taught. He did not believe it. He assumed the sensors were faulty. He recalibrated them, sent them off to be checked, and told his students more than once to box the sensors up and bin them, because clearly they were broken. For years, every time the strange readings came back, the answer was the same. Bad equipment, move on. But the readings would not go away, and if you keep throwing out data because it feels wrong, at some point you have to ask whether it is the instrument that is broken or your own assumption. So in 2021, Sweetman went back. On a return expedition to the same abyssal plain, the team measured the oxygen a completely different way, a separate backup method that did not rely on the sensors he had spent years distrusting, and it showed the same thing. In the dark, the oxygen was rising. That was the moment he stopped explaining it away. Roughly a decade after he first saw it, he accepted that the effect might be real. Not proven, just real enough to publish, and let the rest of science tear at it. And there is one detail here that comes back later. That 2021 expedition, the one that convinced him, was part funded by a deep-sea mining company with a very particular interest in what lay on that seafloor. We will come back to them. If oxygen really was being made down there in the dark, something had to be making it. And here Sweetman and his 15 co-authors offered an idea. Not a proof, an idea. And they said so. The nodules themselves, they found, carry a faint electric charge on their surfaces, voltage on the skin of a rock at the bottom of the ocean. In the paper, published in Nature Geoscience in July of 2024, the team measured surface voltages up to 0.95 volts. That number needs a warning label, and the authors gave it 1. 0.95 volts was the peak, the single highest reading, the outlier. The average across all their measurements was far lower, around 0.024 volts, roughly 40 times smaller. So do not picture every nodule humming at that level. Picture one unusual rock and a whole lot of quieter ones. From that charge came the hypothesis, and the word they used was hypothesize. They proposed that the nodules might act like a natural battery, a geobattery, that the voltage on their surfaces could, in theory, split seawater into hydrogen and oxygen through a process called electrolysis, using nothing but the charge sitting on a rock. A chemist at Northwestern University, Franz Geiger, called it exactly that, a natural geobattery on the seafloor. But splitting water is not easy, and the numbers are unforgiving. The bare thermodynamic minimum to electrolyze water is about 1.23 volts. In practice, once you account for real-world inefficiencies, the figure often quoted is closer to 1.5 volts, roughly the voltage of a household AA battery. Put those side by side, the threshold is at least 1.23 volts. The single best nodule reading was 0.95. Even the outlier falls short, and the average is not remotely close. So how do you get there? The team suggested that nodules sitting together might stack their voltages in series, the way batteries do in a flashlight, adding up until they cross the line. Reasonable sounding and completely unproven. No one measured nodules doing this. It was a proposal to bridge a gap, and the gap was real. So keep two things separate. The reading going up is one claim. The reason it went up, the battery, the electrolysis, the clustering, was offered as a hypothesis, and not one piece of it was demonstrated. That is a very different, much shakier claim. Set the oxygen aside for a moment, because the nodules are extraordinary on their own, and none of what comes next is in dispute. Pick one up. It is heavy for its size, dense, cool, the color of wet charcoal. Cut it open, and you would find rings like a tree. Concentric layers of oxide built up around some tiny seed, a shark tooth, a fragment of shell, a speck of older rock. Layer over layer, mostly manganese and iron, laced through with the metals our modern world is desperate for. Nickel, copper, cobalt. The same metals that go into the batteries in phones and laptops and electric cars. And here is the part that should stop you. Those layers grow at a rate of roughly 1 to 10 millimeters per million years. Per million years. A nodule the size of a potato has been building itself atom by atom for millions of years, in some cases perhaps 10 or 20 million. Among the slowest growing structures anywhere on Earth, older than almost anything you could name. Now think about where they sit, a flat, soft plain of mud, dark and cold and endless. On a surface like that, a nodule is the only hard thing for a creature to hold onto, the only rock in a world of silt. And life takes what it can get. Sponges anchor to them, corals, worms, crustaceans, animals we have no common names for because we have no names for them at all. The Clarion-Clipperton Zone holds thousands of species, and surveys keep pulling up creatures no one has ever cataloged. By some estimates, around 90% of the animals living there are still unknown to science. We are planning to mine a place before we have finished discovering what lives in it. Remember the growth rate, 1 to 10 millimeters per million years. Whatever a mining machine removes from that seafloor is not coming back. Not in your lifetime. Not in 10,000 lifetimes. On any human clock, the damage is permanent, whether or not the oxygen claim holds up. The company. Its name is the Metals Company. Through a subsidiary called Nauru Ocean Resources, or NORI, it holds a contract area in the Clarion-Clipperton Zone. And it was the Metals Company that part funded and commissioned the very fieldwork behind the dark oxygen paper. The experiment happened in their contract area, and their money helped pay for the ship. Then the paper suggested that the rocks they want to mine might be making oxygen in the dark. And the company that paid for the work rejected it. In a public statement, the Metals Company wrote that the extraordinary claims of dark oxygen production in their area, in their words, crumble under scrutiny. They pointed out correctly that they commissioned the work and that their team has access to all the raw data. This is the strange gravity at the center of it all. The mining company funded a study, then became one of its loudest critics, and their objections are not nothing. First, the hydrogen. If you split water by electrolysis, you do not just get oxygen, you get hydrogen too, in a fixed 2-to-1 ratio. It is not optional. It is the other half of the reaction, and no hydrogen was ever measured. The mandatory partner of the process the paper proposed was simply not there in the data. Second, the voltage. The company argued that the highest value in the paper's own plotted dataset was around 0.24 volts, not the 0.95 in the headline, and that even the headline figure is far too low to split seawater at all. Third, and this is the one that stings, the controls. In some of the experiments, chambers were run with no nodules inside at all, empty, and the oxygen rose in those too. If the rocks are supposed to be the battery and the oxygen climbs even when the rocks are absent, then maybe the rocks were never the cause. Maybe the effect is coming from the equipment itself. That is the artifact argument, and it did not come only from the company. A wave of scientific rebuttals followed, roughly 5 of them, from named researchers: Downs, Tangberg, Trelevik, Cuesta and Jaspers, who argued on pure physics that making oxygen this way below 1.23 volts would violate the first and second laws of thermodynamics. Most began as preprints. Then, in December of 2025, the strongest of them landed in a peer-reviewed journal, Frontiers in Marine Science, under a title that says it all. Extraordinary claims require extraordinary evidence. Its conclusion was blunt. The oxygen, they argued, came from the benthic chamber lander itself, the instrument, not the nodules. Critics also noted that earlier studies in these same nodule fields had measured oxygen being consumed, not produced. So the case against looks strong. But before you close the book, remember who is making it. The conflict of interest here does not run one direction. It runs both. The metals company funded the study and then attacked it. But a confirmed finding of dark oxygen would be a public relations catastrophe for a company that wants to mine that exact seafloor, and several of the critics have their own ties to the mining industry. So the funder is not a neutral referee, and neither entirely are some of the critics. There is no clean, disinterested voice in this room. So where does the science actually stand right now? Let me be precise because precision is the point. Sweetman's team still stands by the observation. He has said plainly that they are completely convinced this is a real process and that they will answer their critics through peer-reviewed channels. On the core reading, they have not backed down, but on the mechanism, they have quietly retreated. In a scientific abstract in 2025, the team's language shifted. They stopped saying nodules and started saying manganese oxides, or polymetallic oxides. And on the electrolysis, the geobattery that gave this story its spark, they now say the mechanism is presently unclear. They conceded that some of the chambers in the study contained no nodules at all, only loose particles of manganese oxide. The elegant battery on a rock picture from the headlines has largely dissolved. What remains is the raw claim. In the dark, the oxygen went up. The journal has responded, but carefully. In April of 2026, Nature Geoscience attached an editor's note to the paper, alerting readers that aspects of the article are subject to concerns being considered by the editors, and that a further response will follow. An editor's note is not a retraction. The paper has not been retracted, it has not been debunked, it has been flagged. Those are very different things, and anyone who tells you dark oxygen was disproven is going past the evidence, exactly like anyone who tells you it was confirmed. And the story is not over. Sweetman won roughly £2 million from Japan's Nippon Foundation for a new 3-year project built specifically to test this finding, with plans to survey down to around 11,000 meters using newly built equipment. Some critics have called that funding potentially misallocated, spent chasing an artifact. Others would say it is exactly how science is supposed to work. You make a strange claim, you go back down with better tools, and you try to break it yourself. So here is the honest ledger. Agreed by everyone, the oxygen readings rose in the chambers, contested by everyone. Whether that rise reflects a real process on the seafloor or an artifact of the instruments that measured it. And still missing, after all of it, no independent team has reproduced the result. Until someone does, this stays exactly what it is. A striking, unsettled, unfinished question. Let me take you somewhere speculative now, and I want to be clear that we are stepping off solid ground. Everything here rests on an if. If the finding holds, and it has not yet, the implications would reach a long way past the seafloor. For all of history, our search for life beyond Earth has followed the light. We look for sunlight, for warmth, for photosynthesis, because that is the engine we know. Oxygen has been our signature of the living, and oxygen, we assumed, means something catching the sun. Sweetman himself put it in conditional terms. If oxygen can be produced without photosynthesis, he suggested, it changes how we think about the possibility of life on other planets. Consider the ocean worlds of our own solar system, moons wrapped in ice, hiding liquid oceans that never see a single ray of sun. We have always assumed those black seas were, at best, marginal for life. A mechanism that made oxygen on the floor of a lightless world would quietly rewrite that assumption. But that is a maybe stacked on top of a maybe, speculation and resting on a finding that has not been replicated. Thrilling precisely because it is not yet true. It would be dishonest to hand it to you as anything more. So let me bring us back to what is solid, because you do not need dark oxygen to be real to understand what we stand to lose. Rocks that took millions of years to grow, erased in an instant. Thousands of species, most of them still unknown to us, living on the only hard ground for miles. A seabed that, once the machines pass over it, may not recover for decades if it ever does. None of this is disputed. None of it rests on a contested reading in a sealed chamber. The case for caution was already there, written in the geology, long before anyone saw a number climb where no light reaches. Maybe the seafloor breathes, maybe it does not. We genuinely do not know yet, but we are preparing to strip mine a place we have barely begun to understand, chasing metals for the surface world, while a real question about that same seafloor sits open and unresolved beneath us. The ocean keeps its secrets. It has kept this one for millions of years, layer by layer, in the dark. The least we can do is find out what it is before we take it apart. If you want to keep descending with us into the places the light never reaches and the questions science hasn't closed, stay with the channel and keep exploring the deep. There is so much more down there than we know.